Awesome. Hi, everyone, and thank you so much for attending today's Medical Student Grand Rounds. We have a great talk lined up for you today, but before we get started, I wanted to quickly refamiliarize everyone new and returning to what MSGR is. So MSGR was created last year to acknowledge medical student achievements and passion, and every talk is formatted as with a medical student presenter introduced by an esteemed faculty mentor. We are currently holding them on the first and third Tuesday of each month at noon. We're going through the end of April this year, and we will be via Zoom for the rest of this term. If you love Wu's talk and think you know someone else who might be a good fit to present their work, you can nominate a presenter via the QR code here. And if you're curious to see what else we have lined up for the rest of the year, you can go view our schedule at go.osu.edu/MSGR. And without further ado, I will turn it over to Dr. Tendy Chiang for his introduction.
Hey guys, good afternoon. My name's Tendy Chiang, and I'm a pediatric otolaryngologist and a PI in the Center for Regenerative Medicine at the Research Institute at Nationwide Children's Hospital. Today I have the honor of introducing Yul Byun for his grand rounds entitled Inventing the Future of Medicine, How to Engineer Your Own Medical Device. Wu is a third year and has been a member of our lab for the last year. He has done a tremendous job bringing his expertise in 3D printing to our lab. As background, our lab is devoted to the creation of tissue-engineered trachea for airway reconstruction. We're a multidisciplinary team, and we represent many disciplines, including surgical disciplines, material science, computational modeling, and cell biology. As you know, medicine relies on innovation and invention, and it's important to realize that any member of the healthcare system can identify critical gaps in care and influence change. Wu's talk today will discuss the basic steps of how to translate your invention from concept to the bedside. Please join me in welcoming Wu as our grand round speaker today.
Hey guys, yeah, thank you so much for the great introduction. So my talk is going to be basically an introduction on how to think of new ideas to make a device and going through the process of making the device. And I'll include some information on, near the end about what to do with that idea once you have that device, kind of prototyped out. So this talk will not be focused on, like the intellectual property, classes of devices, the FDA approval process. That's a little bit, that's a whole nother topic. So it won't be on that, although I will go over a little bit. But I really want this to be a introduction level talk on how to really make your own device. I don't just mean like sketching it up, but I mean actually physically making it. But before I start, I just want to kind of go over talking about who I am, just so you guys know who I am. I grew up in a town called Oak Ridge, Tennessee, in Eastern Tennessee. And this place is pretty interesting because it's where they enriched the uranium for the atomic bomb in World War II. It's called a secret city, and it's where there were these secretive, big industrial plants there to enrich the uranium, and no one working there knew what it was until after the war. So I kind of grew up surrounded by all this history and a lot of the engineering and the science that went into that. Otherwise, I did a lot of camping. If you can kind of guess which one I am, this is me and my scout troop. That's me right there. And so after that, I went to Penn to study bioengineering. And while I was there, I mainly worked in a lab that did tissue engineering work. And in this lab, I got to develop my own microfluidic devices and different, incubators and bioreactor devices to help grow these organs. So that's where I got a lot of the skills that I'm going to discuss now. I'm in the top left if you can spy me there. But yeah, it's just more specifically, or more recently, sorry, let me move this little zoom window. I did more clinical work with the Department of Anesthesiology and Critical Care at Penn. And here's me after programming this EEG synchronized device for testing for surgical awareness. Pretty cool and weird study. So more specifically, I want to discuss some of the devices that I came up with. So this is my senior design project where we had this indocyanine green imaging system, and I helped produce the projection system for live operative imaging of tumor boundaries. And on top of that, actually, here's me. Here's me presenting that project. I used to have long hair. We don't talk about that anymore. You know, while I was working in the lab that I was mentioning, the bioengineering lab, I did get a patent out, and I went through the whole process, so I'm a bit familiar with it. And this here you can see that's been filed in Canada, which is kind of interesting. But anyways, so I want to kind of pivot to discussing the devices themselves. So, you know, this is a picture that I took of my classmates during ground school, and we're practicing ultrasound here. And I think the quickest thing that you'll notice when you get into the hospital is there's all these weird, I want to call them toys, but all of these devices everywhere. There's, you know, specific tools for the job. And I really want to emphasize that there's tools being used in every little space in medicine, right? It doesn't have to be super complex or super simple, but it's, you know, they're everywhere. So I have some examples here. Here's a ventricular peritoneal shunt. If your brain has too much fluid, you need to drain that somehow. And you know, they've really ranged in complexity. And here's a more recent one. And people might be more familiar with the continuous glucose monitors. And here's a common Dexcom. And here's something that you see a lot in the hospital, or see all of these in the hospital, but this is a wound vac. And it's just a series of simple tubes connected to a vacuum. And here's what people typically think about when they think medical device. It's like a robotic prosthetic, but you know, it doesn't have to be that complex and specific. So I want to really emphasize a few points here. That is that everyone is an innovator. If you can come up with an idea, if you can look at something and be like, hey, why are we doing it that way, right? You can approach a certain issue and come up with new ideas on how to handle an issue. So I really want to emphasize that this talk is for everyone, and that you sitting right there, you are an innovator. And I also want to emphasize that new perspectives are always valuable, right? The perspective that a long practicing attending has is different than a medicine, it's different than a nurses, it's different than a pre-med shadower, it's different than a volunteer, right? And you know, that's also different than someone who only sees medicine from an outside perspective. And everyone has something unique to think about what's going on. And I really want to emphasize that a lot of these changes, a lot of these new devices come up from someone being like, why do we do it that way? When they ask the question, why do we do it that way? Someone who's familiar with that area might be like, we've always done it this way, but a new perspective is where the ideas are really where they're really coming from. Another point is that the tools to make a device, they're very available, they're affordable. You can just go online and buy them for yourself. And that's what I really want to go through in this talk. Some of the common tools that really help you make a device. And lastly, you're an engineer. I think there's an impression that you have to have studied engineering and done years of engineering and, you know, nerdy, wearing like khaki pants and everything to be an engineer, but I don't think so. If you can come up with an idea and you have some of the basic skills to make something, basically like arts and crafts, right? Then you're an engineer. So I don't want you to devalue yourself and be like, that's not for me. It is for you. So I kind of laid out the basic process of how to make the device. So on the left, a little head with the gears is supposed to be the idea. Let's say you join a new procedure and you're like, hey, you know, maybe this device would be a cool thing that people might need. But of course, you can't just sit on the idea. You have to just do something with it. So I have this fun little art piece in the middle. So it starts with validation, right? And I mean, like, you need to validate. Is this something that I'm the only one that thinks it's needed, right? Am I like misled in how useful my idea is? All the way to, does my prototype actually do what it's supposed to do? Okay, and it's supposed to be a circle kind of feeding it on itself, because you need to make a prototype to really test things out, right? And if it doesn't work out, you need to go back and validate it and kind of fix it up a little bit more. And of course, you always need some early funding to get your prototypes going. There's disclosures and intellectual property concerns. And of course, once you have an actual device and a patent, you know, what do you do with it? Do you license it? Do you make a startup and really handle it all the way? Those are concerns that we'll discuss in a little bit, but not fully. But you know, once that's done, you go through a regulatory process. That's the little checklist, and then you finally get to the patient side where it's actually used. Now, I do want to say that in this talk, I'm going to focus on predominantly validating and making the actual device. And to do that, I want to use an example. So this device here was recently approved. It's called a Sentimag. So it's kind of interesting because what they do to localize breast lesions is, they'll actually image it using radiation and have a wire. They'll have a wire to guide where the lesion is. But of course, that doesn't let you, take out that lesion after the fact, like a long time after. Right after you do that imaging, you have to do it. You have to do it right afterwards. It doesn't let you do it long afterwards, right? So it kind of helps you. It would help you streamline the process if you could actually put like a little marker in the breast where the lesion is, so you can take it out at a future time and also track it, so you know exactly where that lesion is. But it also helps if you could actually take a sentinel node biopsy with a dye that's detectable using the same device in the same process. So what this thing is it's like a magnetic sensor basically that acts upon like a little ferrous bead. They call it, I think, like literally like a seed, right? And they have a solution here with a magnetic nanoparticles that help you detect it using this device. So I'm going to use this as an example device, and I'm going to break it down to two parts. So there's like a physical part. You have to actually build it, right? It's like there's plastic and metal and everything, and then there's also the electronics to it. And I want to emphasize that not all devices have electronics and more complex things to it. They can be really simple, but just in general, this is what most devices are composed of. So I want to go through the process of making something physical and also making the electronics and some easy tools that you can use. So I want to focus on the physical part first. So it's kind of interesting because we've had pretty complex techniques of making things, 3D objects for the longest time. An example is pottery. And specifically, this is coiled clay pottery. And this technique goes back, I think the furthest back that they found evidence of this is maybe like 9,000 years or something like that, where you literally just roll up clay, kind of stack it, coil it, and make any pot shape that you want. And that's literally what 3D printing is. It's like ancient 3D printing. But now we have computers and machines, and they do it for us. So the most commonly used 3D printing method is called fused filament fabrication. That's literally you're making coiled pottery, but it's computerized. You can make all sorts of weird shapes, all sorts of weird contours, let it sit and do the job itself. So the basic concept here is that you turn the little laser pointer here on a heated extruder that melts a bit of plastic. And that plastic, like the coils in the pot, are stacked into whatever contours you want. And to do that, this bed down here will move around. And I'm going to show you a real 3D printer of the different parts in just a second. So this is the printer that I have just in my living room, just for my own hobby and work use. And I'm going to share my second camera. Let's see how well this works. There you go. All right. So this is my 3D printer. So let me just get this wire a little bit lengthened. And I'm just going to go through the parts here. So you see the polymer here. This is what's called PLA. And there's a spool of it, and they come in spools. And you can see it being led through into all of this stuff into the extruder. So let me show you guys. If you can see this little tip here, that's the extruder. It's heated to 200 Celsius right now, but that's where the polymer comes out. So if I were to push in the filament, let me make it a little bit darker. If I were to push that in, you can see the melted polymer coming out. Okay. So that's what makes the coils to make whatever shape you want. And here is the bed that moves around. So this only moves in this axis. The extruder itself moves in this axis. And there's these threads in the back that move the thing up and down. So that's literally what a 3D printer is. And of course, to make make life a little bit easier, there's a little panel there, a little USB, not USB, an SD card slot to load your designs into. So it's a pretty simple device. So I'm gonna go back to my presentation, and then I'll go through how to actually use this thing, right? You're kind of sitting there like, okay, how do I actually use it? So the basic process, there's still polymer coming up, let me clean that up a little bit, is first you have to design what you actually want to print. Okay, and there's different software that I'll go through that you can use to do that. Next, you have to, what you call slice the object. And what that does is literally convert a 3D object that you design into a bunch of coils that 3D printer can follow and produce and make. And you can see in that image, there's actually, looks very much like the coiled clay pottery. And the last step, of course, is to wait and print. And I do want to emphasize that polymers come in all sorts of shapes and polymers. So there's a lot of different things you can do with them. But right now, I just have white loaded into here, and then just blue polymer in the picture. So just very quickly, and I think this will be a good reference if you've never used the software, used these programs before. But to design it, I prefer Solidworks, but you have to pay for it or have like school access to it, so it's a little bit expensive. And there's a bunch of other ones that you can use, but I do want to emphasize these down here. So these are libraries where you can download pre-made designs. So if you want to make like daily useful things, someone has probably made it, designed it, so you can actually just download the file and print it yourself. For more specific uses like medical devices, you'll have to go up here and make things from scratch. And I won't go through that process in this talk, but there's a lot of tutorials online that'll help you make things in 3D. Next, you export that and you slice it. And again, there's a huge list of slicers, and I'll show you one in a second. And then next, you have to use a printer and print it. So I included some of the most common 3D printing brands here. And just as an example, this was last week. I went on Amazon and I found, this is not the exact one that I have, but it's one that's still very good, one of the most popular ones. And it's 240 bucks. You can find ones from anywhere from like less than 100 to thousands of dollars. So the barrier to entry is relatively low, and you can just go online and just buy it. And I got mine at Micro Center, so you can just drive there and get one within like 20 minutes, right? So I do want to emphasize things are very accessible for you. You can literally just have a 3D printer in your living room. Okay, so I want to go through the process of actually using the software. So I'm going to share this window, and what you're seeing right now is Solidworks. So this program here lets you, sketch and make different contours in 3D space. I won't do that here because it's a little bit time consuming, but a program that lets you do that basically looks like this. And then what I'm going to do is export that, or just save as an STL file. That's one of the more common files that you use to like transport, save, download, whatever, design files. So I'm going to save that. And you can see that it'll convert it to a lot of polygons and export it. And then I'm going to share another window of a slicer. So this slicer program is one that's specific. I guess I can say specific, but this was recommended to be used with my printer. So I'm just going to upload. Let's do an open file. That gear file that I just saved. Okay, it's a little bit bigger than I want. So I'm going to scale it down maybe to 50%. And then you can position it so it's on this this mesh, which serves as your bed. And the bed is where, oh, there we go. And the bed is where the thing's going to be printed, and I'll show you that closely in a second. And there are some settings that are really common or are common to 3D printers, and that's layer height, basically how the diameter of the coils that you're laying down. And of course, the finer you get, the more precise your contours get, and you can make finer features, but it takes more time. As you can imagine, you have to lay down more of the thin clay filaments in this case. Infill is how much of that design you fill with polymer. And of course, the lower you go, the less polymer you use. and the lighter it gets, but the weaker it gets. So if you want to do something load bearing, you probably want to do it a little bit higher. If it's not load bearing, it's a little bit more light, small part. Maybe you want to have lower infill. Now, one thing that you'll see often is support. And what that does is if there's any overhang, if you can imagine making clay pottery with an overhang, it's going to start drooping and do weird things. It's hard to do that with an overhang. So support just it just prints a like a column underneath any floating parts so that it doesn't sag. And adhesion is just like a skirt that lets you more easily take the printed object off. But I want to show you this. You can actually get more specific settings, info pattern, how thick your walls are, what materials you're using, what temperatures you're using, how fast the things move around. So there's a lot of settings, whether you have cooling, and they're all to kind of adjust for different polymers, any kind of distortion that you get. But right now, we're gonna just go back to the recommended and keep it really simple. And then that looks pretty good. And we don't need supports because there's no overhang parts. So I'm gonna slice it here. It should be pretty quick. And I'm gonna preview. So it tells you how long it takes and how many grams of plastic it takes. And when I preview it, you can see the little coils that the 3D printer is going to print. So I'm going to save this to a file using a SD card here. And I've already done that just for the sake of fun. And what I'm going to do is go back to my camera. There we go. And then we can start printing. So this bed here is heated so that the plastic as it's laying down doesn't deform as much, doesn't contract, and the plastic sticks to it. But let me just quickly go to this. And since things are heated up, sorry about the glare, maybe this is a little bit better. Clean the polymer a little bit. So it'll get moving soon, but let me just show you something really quickly. You can make pretty complex parts using a 3D printer. So there's the inner ear. What's in the inner ear of the cochlea? Oh, things are moving. So right now it should kind of 0. And then you'll see it touch down onto the bed. To kind of back up a little bit. It's kind of narrow and glary. So it's just tolerancing the print bed. Right now it's just printing some polymer to clear out the nozzle. So it's all prepping it right now. And it's gonna start printing it in just a second. So you can see it's kind of moving in a circular shape, extruding the shape of, in this case, the outline of the gear. So we'll watch it for maybe a minute more. And then see it as it contours the actual gear, I guess the gear shape. Right now it's doing that. So this is laying down the outline of the first layer. So I'm going to show you the top of it from above. And you'll see that kind of can see part of the gear. Now that's a better view. Yeah, so that's how it works. It's relatively simple, but you can make really cool complex shapes like different bones in your neck. I printed those for fun. But yeah, so that's basically what how the 3D printer works. Now I'm going to pause the 3D printer and turn it off because there's a fan running. It's kind of loud. But hopefully that was a pretty cool demonstration of how easy it is. Literally just takes a minute to not make the design file, but download the design file, slice it, and get it printing. So I'm going to stop it and then turn it off because it's a little bit loud. And we'll see it from the top. You can see it from the top there. So if I were to let that go, it'll make the whole gear, but I don't know if you saw that, it'll take 5 hours, so we won't wait for the whole thing. Okay, now going back to the top. I want to go over some of the polymers that we have. So what I used there was polylactic acid, or PLA, and you'll most commonly find that in biocompostable like cookware or like kitchenware, I guess, little cups and forks and spoons and things like that. The thing is, it's rigid, a little bit brittle, but it's biodegradable, so you can't really like let it sit in water. But it's also biodegradable, so it's less there's less impact on the environment. And it melts at 200 Celsius and has a cost per kilogram spool. Another commonly used polymer is ABS, and that's, you'll find that in Legos. So it's kind of like it's a very robust plastic. It's more temperature resistant, but the bad thing about all of these polymers is that they off gas stuff that you don't want to breathe in. So you want to have some ventilation, have the windows open, and as you can see, it starts getting soft at a bit of a higher temperature. And now here's TPU, which is it's a flexible polymer. So you can make, in this case, like people make tubing and AV stuff out of it, but you can make, if you need gaskets or any kind of like, people make soles of their shoes with this kind of stuff. So some cool things that you can do. Now, this is only 3 of them, and there's many more polymers that you can use, but these are some of the more interesting ones, more commonly used ones. And of course, PLA is probably the most common one. It's the most affordable, has the most colors, has good properties, and probably what you'll end up using. Now, there's another type of printing that I want to quickly gloss over, and that's called SLA printing. And I'll tell you what that stands in a minute. But basically what happens is the bed is actually above here, and then this UV laser will cure resin as the bed is moved up, and the UV laser will move around. And they actually have LCD-based ones now. So this is another way. You have to deal with the resin, which is kind of annoying, but another 3D printing technique. It's called stereolithography. So going back to the example device, the magnetic sensor, basically. Let's go over how to make the electronics now. So we made the physical parts, or went over the process of how you'd make such a physical part, but let's go over how you make the electronics. So to do that, you need something called a microcontroller. And what that is a, it's a chip, it's an integrated circuit, but what that is a kind of a simple computer. It's a little bit, it's not as simple as that, but it basically has a processor, some memory, and some circuitry inside that allows it to be programmed and autonomously function. But if you can imagine, if you were to try to make something with this little chip, you have to be careful of the little prongs, you have to solder them somehow, you have a circuit board that you make all the way, and it's a very annoying process. So to make a microcontroller more usable, there's something called an Arduino. And there's different types, Arduino is actually a brand name, and there's different types that you can find. But Arduino, I think, is one of the more commonly used ones, especially in school and for hobbyists. But it's one of the easiest and well-supported ones. So basically what this is, you can see the same chip that's here, right here. And there's ones with more or simpler or more complicated parts. But you can see that chip here, and it's put into this chip that's a little bit easier to handle. So there's these prongs where you can insert wires. There's a USB port, power jack. So you use a USB port to program this thing, and then you connect wires to the little ports, and then you basically can program the electronics to do whatever you want it to do. So this is a very important tool, very useful tool. And I just want to show this. So Adafruit is kind of like a hobbyist website where you can buy a lot of these parts, and they really popularized accessible electronics. So it's definitely worth finding out. And that's the founder of Adafruit. And I just want to show you guys that there's all shapes and sizes and functions of these microcontroller chips. There's ones that are wearable, which is very, very nice. I think this is the scale I approximately. And another thing that I want to show you guys are these shields. So these shields are basically chips that plug into Arduinos, and they have their own functionality. So you can see the Arduino thing down here, and this shield on top. You can see that the outline of them are very similar. So these guys have specific functions. So this one and this one is a RFID shield. So it's like the name tag, like your credit cards and things like that, right? This is I believe a GPS shield. This is a Wi-Fi shield, and this is an LCD shield. So If you want any kind of more complex functionality, well, these exist. You can just buy them and plug them in, right? Very simple to use. And just to emphasize that, I added some some animations to really make the point that these are very useful tools. Makes it a lot less intimidating to build in more complex functionality. And they always come with tutorials and scripts that you can use. Now, how do you actually do this? So first you design the circuit and make the circuit. And we'll do a quick example circuit right now. And you program it, right? So this little thing here is called the Integrated Development Environment for Arduinos. And it lets you program in these areas, and I'll show you what they do, and upload them through USB onto an Arduino. So you can very easily make changes, upload the script, and get your machine working and doing what you want it to do. And of course, the last thing is just to run the script and see if it works, and then just maybe put in like a more permanent, solder things together in a more permanent I guess make it more permanent, and then put it into like a 3D printed machine device that you just made. So we're gonna do a quick exercise here, but I just want to show you the parts that I'll be personally using. So I have a type of Arduino. It's a little bit better than the one that I showed you before. And the price changes, so I put it in the amount that it was on their website. But of course, you can get cheaper Arduinos, and there's like not off-brand Arduinos that are cheaper, like way cheaper. You can buy these little electronics kits for $20 or less. More complex ones exist, but there's basic ones with resistors, breadboards, and things like that. And here I have a Hall effect sensor, which is which detects changes in magnetic field that was only $2. So I'm gonna use these parts, and I'll try to make a circuit right now, which is going to be a little bit interesting, but we'll see if that can be done. So I'm gonna move the camera here real quick. Okay. So and I'm gonna move to the start sharing my camera view. So this is kind of what we're working with. Literally a breadboard. So if you guys haven't seen these before, they just let you plug in wires really easily and make circuits that are non-permanent. So you don't have to solder. And they have like adhesives in the back, so you can just stick them wherever. But basically, in this view, any vertical line is connected. So these electrodes are all connected. These are horizontally connected. And we have the Arduino here connected to a USB cable. Now I want to show you a few things. So you can see a chip in the middle, but what you'll see here is, let me actually use a wire as a pointer. You can see different leads. You can see a ground lead here, a bunch of different leads, PWM, digital leads, analog leads. So I won't go over what those mean, but there's a lot of things you can connect to this guy, right? There's a voltage sources and more ground. And of course, there's a DC port in the back here. So if you want to have your device powered by itself and not connected to USB, you can. So I'm going to make a quick, very simple circuit that'll just turn on an LED. So let me go through that right now. So, when I'm looking at this, I'm going to ground the thing first. So there's a ground lead here. Let's put it maybe here. Actually, let's put it right there. And then I have a little LED. Let me fumble on a little bit more. A little LED, and I'm just going to connect it. Let's do it up here. So this row is all connected to each other. I have a resistor. So, oops, and I just dropped it. All right, my hands are cold, so I'm fumbling around here. And a resistor. And to power it, I'm going to connect it to lead, let's say 13. So I'm going to connect or share screen with you so this is a really simple LED circuit, and we'll see if it works. I'll bend this toward you so you can see the LED a little bit better. All right. So the environment where you program the Arduino looks like this. Let me make it a little bit bigger for you guys. So you can see, I can connect to the specific board that I have through a USB. It's connected to my USB that's connected to the Arduino. So how this works in this case, you can always find tutorials and find scripts that other people have written. And I highly recommend that you do that because it's a lot easier to do that. But basically, you have a little section here to set up code. Basically, you run it once. And in this case, we're going to set pin 13 as output, right? So that tells the Arduino, hey, this is where you turn on the voltage when you're told to. Now, there's this loop here that's going to run continuously, and that's one way how the Arduino runs autonomously, where it just keeps on running a section of code over and over again. And of course, you can make it really complex with like interrupts and different loops. But right now, we're going to do a relatively simple script. So I'm going to do. This is how you turn on a lead. So I'm going to turn on the LED, wait 1,000 milliseconds, just a second, and then turn it off again, and then wait a second more. So it's just gonna flash an LED. But let me just double check because there's a little error here. Coding live makes me sweat, but I'm doing it. So let's upload it. It's asking me to save it, and it's done uploading. So you can probably see. Let me share the LED camera. Oh yeah, you can see that thing just flashed. Super simple script, and we just made an LED flash. So that's going to become our indicator LED. And right now I'm going to make a more complex circuit that includes the Hall effect sensor. So this guy here detects changes in magnetic field. The specific polarity, I won't really go into that because it's a little bit confusing. But I'm going to face it maybe here. Actually, let's get it a little bit closer to the chip, to the Arduino. Okay, so there's our Hall effect sensor. It needs a resistor. Let's actually put it here. And it needs to be grounded. So I'm going to connect another ground lead. All right, and then what it needs is a high voltage or a 5 volt. I might have flipped that, but let's see if that actually works. And then it needs one electrode to go into the Arduino. So, all right, let's see if that actually works. If it doesn't, we'll troubleshoot for a few minutes, but anyways. So I'm gonna go back to the IDE where we program it. So I'm gonna set, we plugged the sensor into lead 12. I'm just confirming that right now. Okay, so I'm gonna set that to input. So the Arduino is gonna use that to detect things. And I like to have my things in order just because it makes things look a little bit nicer. Okay, so that's the input now. Now I'm gonna use what's called a while loop, right? So I'm gonna say while. So this reads the pin. Well, it's low. The low and high has to do with the exact north or south, but we won't go into that now. So basically what this does is if it detects one of the polarities is close and has changed to be that polarity, then it'll turn on the LED. And then it's gonna turn it on for a second and then turn it back off. Let me just make sure this is correct. All right. So I'm gonna upload it again. Oh, and it's so if I make an error, right? It tells you that you did something wrong and where it went wrong. So that's why these IDEs are really helpful. Where you can just write code and it tells you where you went wrong. And there's different settings there. So I'm gonna go back to the camera. And let's make sure that okay, so I have this fridge magnet, literally ripped it off of fridge magnet like 5 minutes before the talk. So I'm gonna bring it close to the sensor. And then I don't know what poles are. Oh, there we go. It detected it, had it on for a second, detected it, on for a second, And I guess it keeps on detecting it. Yeah, it's like while. But yeah, so we very easily made a magnetic sensor. Now, we could actually modify this a little bit more and have it so it detects the actual strength of the magnet. And we could add different shields and have it like wirelessly connected, but you basically build things step by step, and suddenly you have a more complex set of electronics that does whatever you want it to do. So hopefully, hopefully that was kind of like a useful demonstration of how accessible and how easy and how quick making such a thing is. And I just did it using these pretty affordable parts. And again, you can make this a lot cheaper if you want to, because there's about 100 times of this I didn't use, right? 100 times more than what I actually used. So yeah, just in summary, you know, we, of course, it's like the thing that we just made is nowhere near as complex as this. We didn't even print one gear, and I don't know if there's a gear in here, but we made like a magnetism sensor. But you know, I just want to make the point that, you know, you can make something physical and make the electronics very easily nowadays. So we made both of those two parts. So going back to the big picture. So it's like logistically, what do you do after you have a prototype going, right? You have an idea and a prototype going. And I want to discuss that a little bit more, which is like these parts here. So I do want to say that this is a whole nother field, but so there's a lot of information out there, and I don't want to get lost in that now. But I just want to give you a quick overview of what's here at OSU and what's here nationally. Something that's more accessible for, in this case, students, but also clinicians. So one resource at OSU that I find very impressive is the Innovation Studio, and it was started by the College of Nursing. And this is really interesting because they actually offer pitch competitions where they'll give you a few $100 to fund your initial idea. Right? And then there's different stages of that, so you can actually get more funding. And they offer this space, which I believe used to move around. I don't know what happened with COVID, but it's this innovation space where you can make just tools, resources that you can sit here and use, which I think is a fantastic, genius idea. You need something like that in the med school. Let me get on that. But anyways, so another resource that's coming up soon is the EdTech Incubator, and I'm on the steering committee for this, and this is going to be at the Health Sciences Library. A lot of you guys have probably noticed that, you know, the cool windowed space areas are no longer available. That's because we have these cool 3D printers. So it's going to be a place to learn and hold workshops and things like that. And then, of course, nationally, there's things like Inventors Competitions. A lot of schools will actually run these, and there's things like hackathons that you can just go to and start making things. So I think it's a good exercise to really look into. If you just Google Inventors Competition or medical device competition or, you know, student inventor competition or whatever, just Google something, then a lot of these will come up. But this is one of the more prominent ones here, the Collegiate Inventors Competition. And I knew a lot of friends and classmates who actually competed here and actually placed, which is pretty impressive. So yeah. Now, just a few last things. I won't go into these topics in too much detail, but you know, once you have this idea, once you have this thing that's kind of fleshed out, what do you do with it? Do you just sit on it? Do you show your friends? Well, yeah, but like, what do you do with it? You have to really mobilize it and do something useful with it. And that's what tech transfer offices are for. So these guys exist mainly in universities, but can exist in other big bodies, big organizations. And what they do is they help you take your research or your cool device idea, and have a disclosure so that they can actually access that invention and your ideas on it, assess it to see how useful it is, how promising it is, help you file things like patents. You know, if you want to file like a provisional application, they'll help you do that. They'll help you find the resources to really get it going, right? If it's a promising idea. And then they can even help you with things like marketing and connections to industry or private parties that want something like that. And they'll also give you guidance on how to make a startup or license and fully commercialize that idea. So maybe that's a little bit promising for most inventions, to be honest, but you can, they'll take you far. And here specifically at OSU, they have what's called the Inventor's Guide to Technology Transfer, and it's a PDF that's on this page. And it's probably the most useful single document for going through this process. And most universities will have their own guide. And of course, since you're working with the university, they'll have some ownership of your idea if you agree to disclose everything and work with them. But it's a pretty good deal on your side, because you get to get professional help to take your invention to the next step. And I don't want to not emphasize this enough, but the US Patent and Trademark Office has their own resources to help you out. And they're more useful from the perspective of, is your invention novel? Is this is this new intellectual property? And what can you do with it in terms of patents, right? So I won't go into the type of patents, and there's ones for like plants and things like that, but I won't go into that. But there are pages and pages of information on how you can evaluate your own idea and get to the patent process and go through it. So this is definitely a resource that's underestimated, and you should check out if you're interested, and it'll give you a better idea of what goes on. And I also want to talk about the FDA page, but it's already we're already 15 minutes in, so I won't do that. But FDA will have their own pages on things like the approval process for devices, and that's a good resource to look at. Good resource to look into if you're planning further than just the device and licensing it out. And lastly, we have a black mirror here. So if you're looking at a phone or something, you can probably see yourself in it. And I do want to emphasize that you are the person who can invent the future. You have access to these resources. You have the basic skills to build upon now, right? And you have the unique perspectives to use to make new ideas and make new devices. And I really want to emphasize that anyone watching this can make something new, can invent the future. And yeah, that's the rest. That's all of my talk. And the rest of this will be any questions you guys have. And I want you guys to check out this website where you can register, look at the schedule, and provide feedback on these talks.
Thank you, Wu, so much for that incredible and really cool talk. As a non-engineer, it was really nice to be able to kind of follow all of your demos and everything. So we'll take questions now. So feel free to type into the Q&A or raise your hand to unmute if you're comfortable. Oh, someone did message us, Wu, saying your talk was very interesting and inspirational. Thank you for sharing your expertise. And I agree completely. We can just hang out and let people ask questions if they have any.
Oh, it is. Okay. I couldn't figure out how to actually get it downloaded, but that's good to know. Actually,
go
yeah,
ahead.
go ahead. I wasn't gonna say anything more. Yeah, go ahead.
So someone did ask if this recording will be made available, and yes, with Wu's permission, which I believe he already gave, these talks will be uploaded to the Medical Student Grand Rounds YouTube at least a day or two after the talk. So if you go to YouTube and search OSU Com Medical Student Grand Rounds, we have our own dedicated YouTube channel.
And if you guys have any questions or want a copy of these slides, yeah, no problem. Thank you for listening in. But if you guys want a copy of the slides or any additional information, feel free to reach out to me. You can just, I don't know, message me on Twitter, do whatever you want. Just reach out to me, and I can send you any resources that I have and these slides if you want. The slides will have different links actually in the description, and if you want to download some programs, then it's very easy to just look on the slide and get the program. So just let me know. Yeah, thank you guys. Oh yeah, so so I'm working with Dr. Danforth on the EdTech incubator, but we have a lot of different spaces, and we can just talk about a little bit more. So we will have an anatomy visualization space, and of course our fantastic Dr. Quinn is also involved in that. We have VR resources there, and that's very useful for like simulations and training exercises, and Dr. Danforth is the one that's really spearheading that. And we have different hybrid learning spaces and different resources for different, I guess, modalities of learning. So that's going to be coming up soon, but we have a website. So if you guys go on that, if you search up EdTech Incubator OSU, then it'll come up. Let's see.
I wasn't aware that this incubator existed until your talk, so thank you for bringing it up.
Yeah, you're gonna hear a lot more about it in a year. Awesome. Well, if there aren't any more questions, then I think we can just conclude. But yeah, thank you guys for coming and listening. I hope you guys learned some important and useful skills to build upon. And just let me know if you guys have any more questions.
You are the best, Wu. Thank you for such a great talk. Bye, everyone.